Hey, what's up? It's Matt, and in my video on conjecture that I uploaded today, I talked about the birthday paradox. The idea that if there are 23 people together, the odds that at least two of them, share the same birthday are greater than 50%. And this video is basically going to be using some of the math I did in that video to solve another related type of problem. So you don't have to watch that video first, but I feel like it makes sense for you to. So what I'm going to do is I'm actually going to make me smaller here so you can see what I'm doing in Photoshop. I'll leave me like that. And now I'm just going to start drawing some of this stuff out. So, wrong, is that the right button? There, that's what I'm looking for. So, in the video on the birthday paradox, right, I was talking about how person 1, when this person enters the room, they'd have a 365 out of 365 chance of having a unique birthday, right? Person 2 would have a 364 out of 365 chance because this person's already here. Person 3 would have 363 out of 365, and so on, right? So the question I want to talk about in this video was actually inspired by a post I saw on Reddit, and I'll link to that in the description. But the question I want to look at for this video, I'll just write it out too. How many times do you have to roll a die to get every number at least once? Great. So that's the question I want to look at, right? And at first I approached it the same way I did the birthday problem over here. I thought, okay, so for the very first roll, you have a 6 out of 6 chance of getting a number that you haven't gotten before, right? It doesn't even matter what the number is, that's how it's going to work. Now on roll 2, you're going to have a 5 out of 6 chance of getting a new number that you need, right? Now, obviously you can see where this is going. Roll 3 is 4 out of 6. Roll 4 is 3 out of 6. I ran out of space. Roll 5 is 2 out of 6. And roll 6 is 1 out of 6. Now, if you multiply all these together, what you get are the odds that you get every single number in your first 6 rolls. So every number in first 6 rolls. But the question isn't what are the odds you're going to roll every number in the first 6 rolls, it's how many times, I should have written this before, how many times on average do you need to roll the die to get each result at least once, right? So another way we could say that is, what is the expected time we would have to wait, the expected amount of rolls it would take to get all 6 numbers. So here's how we can start looking at this. I'm actually going to erase a lot of this stuff and I'm going to rewrite it. So let's do that. I'll also erase these. Okay, so if the first number, I'll just write like number 1, has a probability of 6 over 6, right? I'm just going to rewrite this, number 2. The expected wait time to get the very first number, that doesn't change at all. It's 6 over 6, right? But for this next one, the odds we get a second number, a new one, as in the odds we don't get this one, is 5 over 6, right? So it's not a 100% chance. And what that means is if we had to expect a certain amount of rolls to get it, because it's not 100%, our expected roll value should be higher than 1. And actually, if we just flip it, 6 over 5, that's the amount of rolls we should expect to need to get the second unique number, right? This obviously won't happen all the time, and you can't have 6 over 5 rolls because that's not an integer, but in terms of like probability theory and expectations, that's when we should expect to get the second number. And then same deal for the rest of these. We can just flip them and say, okay, there's a 4 out of 6 chance we get this next number. That means it would take an expected amount of rolls. It would take 6 over 4 expected rolls. This one would take 6 over 3, this one would take 6 over 2, and this one would take 6 over 1. And so I should have done this beforehand, but if you add all these together, you'll see that, let me actually just Wolfram alpha this really quickly, and then I'll tell you what we get when we add all these together. Great, so I looked it up, should have had that done before, and the answer is 14.7. And just out of curiosity, I have a die here, let's just do it once to see what we get. Okay, first roll, 6. Second roll, 2. Off to a good start. Oh no, I dropped it. Third roll, 4. That's pretty good. Oh wow. Fourth roll, 5. We only need a 1 and a 3 now. And I just got a 1. Alright, well. 5. Oh my god, dude. 3! Finally! Okay, so, as it turns out, even though we got the first 5 in the first 5 rolls, we needed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 to get all 6. So this 14.7, wow, that was bad. This 14.7 as an average here, that's an average, right? You're not guaranteed to need 14.7. You might need more than that. You might need less than it. But that's the expected average of the time it would take. The last thing I want to show is that, I'm actually going to erase this bottom part. So when I was figuring this out on my own, this is something I just figured out. I didn't look it up, right? I looked it up to see if the answer was right, but in terms of the methodology with finding the expected odds and then just flipping them to find the expected time, that was something I looked up on my own. And let me just move this down. Yeah, okay, cool. So something else cool that I found is there's, in the Reddit explanation that I read that inspired this problem, someone mentioned this idea of harmonic numbers. And a harmonic number, without like getting too in-depth with the explanation, essentially it's something you can multiply your numbers by to find the answer to this question. So let me just delete this here to save space. Oh crap, that's not what I meant to do. Here we go. Right, so let's get rid of this. And so essentially, okay. So we can solve this question of how long would it take to get all 6 numbers by multiplying 6 by 6 is the harmonic number for 6. And the harmonic number is equal to 1 plus 1 over 2 plus 1 over 3 plus 1 over, 1 over 4 until you eventually get to 1 over x, whatever number you have for x here. So for 6, this would be, the harmonic number would be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6. That's the harmonic number, right? And then to find the expected wait time for a problem like this, we'd multiply this by 6. And so here's what happens when we do this. We get 6 plus 6 over 2 plus 6 over 3 plus 6 over 4 plus 6 over 5 plus 6 over 6. Or we could rewrite that last thing as 1. And check this out. This is this sort of like mathematical way, one of the mathematical ways to solve this problem. And it's something I didn't know about at all as I did these calculations here. But look, these, hang on, I'm going to change the color. These are the exact same thing, right? Like 6 over 4 to 6 over 4, 6 over 3 to 6 over 3, 6 over 2 to 6 over 2, and then 6 over 1 to 6, or just 6 over 1 again. This is the exact same thing as what I did down here. And I did this down here just by sort of intuitive guessing, or like educated guessing, I guess, taking the expected odds and then flipping them to get the expected time, and it turned out to be the official way to do it. It turned out to equal the number of times its harmonic number. So that was all I wanted to show, just the fact that I inadvertently found one of, I'm sure, many proofs for how to solve this type of problem, and that was really fun because I wasn't expecting to find the official way, or at least learn about harmonic numbers while I did it. So that was pretty cool, and it relates a lot to the birthday problem, but I decided to not put it in the main video because, I mean, you saw how much time this took me here, and I wanted to get out a video as soon as I could. So it's here for you, the dedicated person watching lots of not efficient edit parts of me rambling on in this video. So thanks for watching this video, and yeah, see you soon. Don't know what else to say, but that should be good.